Hello and welcome to this Isaac Physics online tutorial. My name's Michael Conterio and I'm going to be your tutor for this afternoon. What we're going to be doing is we're going to be going through some of the exponentials questions as a follow-up to the exponentials workshop that we've run in various places across the country. If there are any exercises in that you're still unsure about, what you should do is you should make sure that you're logged into Isaac Physics, and then you should use the box below this video in order to send me a message. Bear in mind that those messages will take a little while to arrive, so don't worry if it doesn't seem like I've seen them. I have. And also it'd be nice if you're watching, even if you don't have a message yet, if you could just say hello via that chat box, just so that I can make sure that it's working. So that would be quite useful as well. So as I say, this is a follow-up to the Isaac Physics Exponentials workshop, and what we'll be doing is I'm going to be sharing my screen with you, and I'm going to be working my way through some of the later problems, the ones which actually have been put in there to do at the post-workshop online tutorial. So I am just going to share my screen with you so you can see what I'm working on. There we go. And I am going to start with exercise 8, which is a bouncing ball. It says a ball is dropped from an initial height h0 onto a table such that the height of the bounce is h1 equals alpha h0. Draw a diagram showing several bounces. And that's good advice just in general. Whenever you get a physics question, start off by drawing a diagram to explain the situation. So I'm going to do this, and I'm going to do it so that as we go further along here, time increases. So initially we have ball, which is a height h0 above the ground, and that is at t equals 0. And then after the first bounce, it then ends up at a height h1 equals alpha h0. So it's going to come down here and then bounce back up again, and then comes down here, bounces back up again, but this time to a height h2, which is equal to alpha h1, which is equal to alpha squared h0. And then we'll just draw another one on here, h3, which is alpha cubed h0. So there's my diagram to start off. Okay, so we've got that there. And the first part of the question says, using the properties of exponentials and logarithms, show that the height of the nth bounce is, because the function of n is h underscore n, is h0 e to the power cn, and give an expression for the constant c. Reassure yourself that this is a decaying function. So as you can see, h0 is h0, but that can also be written as h0 equals alpha naught h0, and I've got alpha 1 h0, alpha 2, alpha squared h0, alpha 3 cubed h0. So we get hn, hn equals alpha to the power of n h0. And we're told that we want to show that it's the same as h0 e to the power of cn. So cancelling out the h0s, we get alpha to the power n equals e to the power of cn. So we can rewrite that as alpha n equals EC all to the power n. Alpha is e raised to the power c. Take natural logs of both sides. Get ln alpha equals c. The important thing to remember here is alpha is less, oops, not less than not, sorry. Alpha is less than 1. There we go. So the next part of the problem, let me get rid of that. Next part of the problem says, how far does the ball travel before it stops bouncing in the ideal case? Why might this distance not be attained in practice? So what we're going to do is we're going to look at how far the ball travels. Let's start from the very beginning, and I'm going to call the total distance capital H. So capital H is equal to H naught that it falls down, and it bounces up a distance H1, then down a distance H1, then up H2, then down H2, then up H3, down H3, and so on and so forth. And so we can rewrite that. We kind of want to rewrite this as all the same thing. And obviously we've got 2H1, 2H2, 2H3. But we've also only got 1H0. So what we can do is you can rewrite this as 2 and then we got H0 plus H1 plus H2 all the way to infinity, and another minus H0 at the end. So we've got our 2H0 that we started with here, minus H0 gives us this H0. And we can rewrite this in terms of alpha and n. So that's 2, bringing the H0 out of here, out of the brackets. 1 plus alpha squared plus alpha cubed at the top. And we've still got this minus H0 at the end. So that's H. Now, we don't like this infinite series. We want to get rid of it. But we can see that each term is just alpha times the previous term. So if we multiply everything by alpha, we get alpha H equal to 2H0 alpha plus alpha squared, alpha cubed, and so on, minus alpha H0. So I'm going to label these equations 1 and 2, and I'm going to deduct 1 from the other. So 1 minus 2 gives me capital H minus alpha capital H is equal to. Now, this 2H0 that we have at the start doesn't have an equivalent here, so we get 2H0. Then all these other terms here inside the infinite sequence that we've got here cancel out. So this alpha squared minus alpha squared, alpha cubed minus alpha cubed, and so on until infinity. Then we're just left with this minus H0 and minus alpha H0, which is plus alpha H0. Rearranging, 1 minus alpha times this capital H is equal to H0 1 plus alpha. And that gives us our final result for the distance the ball travels, H0 1 plus alpha divided by 1 minus alpha. Okay, and the reason why it might not reach this in real life is because this is assumed that we always have perfect bounces and effectively treating the ball as a point. We're not losing any other energy apart from when we hit the surface, so we've got no air resistance. So there's a few different things that might mean that the distance we get is actually less than this. Okay. Now the next question, part C. Find the time between the nth and the n+1th bounces. Show that it can be written as 2t0 e to the minus beta n and give expressions for t0 and beta. Find the total time spent bouncing in the ideal case. How many bounces does the ball execute in this time? So we've got a few different things here. But basically what we're saying is the time between bounces. So that's the time going up plus the time going down. So this and this are T1, this and the next bit are T2. So this, the distance that the ball bounces upwards and the distance the ball falls are the same. So let's look. Well, and also for each of these, you can see that we've got. Actually, I'm going to actually call these 2T1 and 2T2, just because we know that the time for the ball to go up here and the time to fall down here, the same distance, have to be the same, and the same with this bit. And so that means that this first drop is a time that I'm going to label T0, which is going to turn out to be the T0 that we actually want in the question. So here we've got our time for between the first bounce and the second bounce is 2t1. And we can see, if we look just at this bit, we've got an acceleration downwards of g going a distance h1. And I'm going to take downwards to be positive just because it's going to be easier. And so we get, and also just going to label this bit t1 as well. T1 is also t1. And we know that it starts at the top of its bounce with u equals 0. So I can use the Suvat equation. S equals ut is a half a t squared. And so this is going to be our hn equal to, our u is 0, so this is 0 plus g over 2. And then we have our tn squared. Now I've gone to the more generic notation, n, rather than doing it specifically for t1, but that's because this situation is basically, apart from the height being different, it's the same for all of these different bounces. So from here, rearranging this, get Tn equals 2hn over g. And rewriting that, we get 2 alpha to the n h0 over g equals 2h0 over g, and then taking this alpha n out, get alpha n over 2 because we're taking the square root of it. And so that's to alpha n over 2 t0. And we've said that the time between two bounces equals 2Tn equals 2 T0 alpha n over 2. And we're showing that this can be written as 2 T0 e to the minus beta n. So obviously there we've got alpha to the power n over 2 equals e to the minus n alpha half e to the minus beta. And taking natural logs of both of these sides, we can find beta. And remember, if you're having any trouble with any bit of this, following any bit of these explanations, do let me know, and I'll try and go over that bit again. Okay. So now we've got T0, T1, T1, T2, T2, T3, and so on. And now we want to find our total time. And this is obviously going to be a very similar method. We have T0 plus 2T1 plus 2T2, and so on and so forth. And we've also just said that Tn is equal to alpha n over 2 T0. So we can rewrite this 2T0 plus 2T1 plus 2T2, and then a minus T0 at the end. Or taking 2T0 out, 1 plus alpha to the power half plus alpha to the power half squared. This is a bit of an odd way of writing it, but I'm trying to just show that the factor each time is root alpha this time, rather than alpha. Multiply both sides by this factor. Same thing again. We're missing the term at the start, but everything else inside the brackets is the same. And end up with minus square root alpha T0. Taking, put the T here, just make this clearer. So calling these equations 3 and 4, and going 3 minus 4 gets us T1 minus root alpha equals 2 T0 minus T0 plus root alpha T0, and that way T equals T0 1 plus root alpha by 1 minus root alpha. So very, very similar, except now we've got root alpha rather than alpha, and we can rewrite our T0 in terms of what we had before. For our time value. And inside here, you've actually got what would be an infinite number of bounces. This doesn't happen in real life. Compression of the ball takes a finite time, it's not instantaneous. And the time that it takes is actually given by the time that sound waves can travel through the ball. And as before, we lose energy through air resistance too. The final bit of this, calculate the frequency of bouncing heard as a function of bounce number of n and also of time tn at the nth bounce. So frequency of nth bounce is just inversely proportional to the time taken for that bounce. So we're using the same definitions, so T0, T1, T1, T2, and so on. And from before, this gives us 1 over 2 alpha n over 2 T0. So we now need to convert this 2 alpha n over 2 into a time. And going from earlier, we're going to find a time tn, which is the time to the start of bounce n. So that's T0 plus 2T1 plus 2T2 all the way up to plus 2T n minus 1. And then your minus T0, and then rearranging that again, we get 2T0, 1 plus alpha plus square root of alpha squared, and so on up until alpha to the power of n minus 1, and a minus T0 because I've gone from T0 to 2T0 here. Multiplying both sides again by the square root of alpha. And then we also get a plus square root of alpha to the power of n inside these brackets. So adding those equations together, 1 minus, so subtracting, I don't know, actually write this down, otherwise I'll get confused. So then we've got 5 minus 6 gives us 1 minus alpha tn is equal to 2T0 minus T0 minus this new one, root 2T0 root alpha to the n, and then plus root alpha T0. Rearranging that, 1 minus root alpha Tn is equal to T0 1 plus root alpha minus 2 alpha n over 2. And so you can rearrange that to get 2 alpha n over 2 goes up Tn, and substitute it back in there. And you'll find that as the time tends towards the maximum total time of the bouncing, your Tn goes to your final time t, and your frequency tends to infinity. So the frequency diverges in a finite time. And this is something that you'll probably experience there. And you drop something and it bounces, you go dum 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 dum, and you hear the frequency increase rapidly and disappear out of the range of your hearing. And so now I'm going to finish off by going on to the next problem from the sheet. The next problem is money revisited, exercise 9. A sum of money M is invested with an interest rate of P%. Banks can choose how often throughout the year to calculate the interest and whether or not to compound the interest. For example, interest might be calculated annually, quarterly, monthly, or continuously. I am going to skip straight to a little bit later where it says, give an algebraic expression for how much your money is worth after T years when the interest is compounded N times a year. So each time period of 1 in a year income increases by P over N%. So, which is the same as multiplying it. So 1 plus P over 100N, because P is the number of percent, so P divided by 100 gives you the correct fraction for that, and N is the number of times a year that it gets done. So obviously if it was 2 times a year, you'd get half the interest there. Then we have to think about how many time periods are in a year. So obviously there are N of these per year. So in T years, Tn time periods. So afterwards, your final money is equal to your initial money multiplied by this vector to the power Tn. Now, if we want continuous, which is the next part of the question, we basically have n going to infinity. So m divided by m naught equal to the limit of n tending to infinity, 1 plus p over 100 n to the power of n. And I'm going to just take the t out there. But this is the same form as what you've just been given, which is e to the x is the limit as n tends to 100, n tends to infinity, sorry, 1 plus x over n n. So we can rewrite this bit here as e to the power of, and our x is this divided by n, so we've got p divided by 100. Now we've still got our t. So we actually have our exponential growth, e to the power of pt over 100. And now I'm going to skip to the very end. Let me say, if M is a capital of a charity, payments are being made at a rate Q, and interest is accruing at a rate of P%, what is M as a function of T? Its capital is initially M naught. This follows on from the exercise at the end of exercise 4. So our rate of change of capital, dm over dt, how our money changes with time, is equal to p m over 100. That's the interest we get on our money m, p%. We also have the minus q, which is the payment rate. And that doesn't depend on the amount of money that we have. That's just the rate of payments. This one is a percentage. rate of the money that we have, so it has the m there. So we can rewrite this. Now there are two different ways of doing this. What you can do is do this as an indefinite integral, and then you can put in your constant of integration afterwards and say, well, at time t equals 0, the capital is initially m0. Or we can put the limits in right now, and so technically these should all have dashes on. We're going from t dash equals 0, the initial time, to t dash equals just t, our final time. And we're going from m dash equals m naught, our initial money, to m dash equals m, our final amount. And integration on the right side is dead easy. You just get t dash from t dash equals naught, t dash equals t. So a bit more complicated, but actually, because you've got your m dash at the bottom here, you get, we can basically do a substitution for this entire in the bottom, which basically gives us an extra 100 over p at the front. And then we just have d, whatever we've substituted in. I'm not explaining this very well, so let's do it properly. I'll actually, let us pick a thing. U equals p m dash over 100 minus q. So du over dm dash is equal to p over 100. So our dm dash is equal to du 100 over p. So we get 100 over p du over u. And we go from u equals p m naught over 100 minus q to u equals p m over 100 minus q, and that is equal to t on the other side. Get 100 over p ln u with the same limits. And then you just have to rearrange to get your answer in terms of this m here. So there you go. I hope that was useful. You can still use the contact us form on the website if you have any further questions. And I do encourage you to use the website in general. Go to isaacphysics.org, have a go at questions. Just pick a question board, one of our top boards, or build one of your own. If you want to try questions from a particular topic, like dynamics or circuits or whatever you like. Yeah, give that a go. Remembering doing a little bit of physics practice often is a lot better than trying to binge physics. And we hope you enjoy using our stuff in the future. Thank you very much. Hopefully see you at another event soon. Bye-bye.